Now, what I've just taught you would have been a standard introduction to radians in, like, say, an Algebra 2 course. But as you progress through maths, or if you study physics, you're going to encounter radians more and more, and they're going to seem to have some sort of strange power, as whenever you're dealing with angle quantities, you're encouraged to use radians rather than degrees, and especially when multiplying them by linear quantities. In fact, you can only use radians in those situations. And one place that radians come up that I found interesting is in Taylor series. Here I have the Taylor series for cosine of x, and what you might notice is you may naturally just use radians here, but you may notice that if you use degrees, you would get a radically different answer. Now, you're supposed to use radians, but the fact that using degrees in this formula implies that somewhere in the derivation of our Taylor series, we relied completely on our radian. But where? Now, when I first noticed this, it took me a while to actually figure out exactly where we assumed radians. But I'm going to save you the time and just tell you that it's in the derivative formulas of our trig functions. Here is the derivative of sine, and it's nice and simple. But it might surprise you that, or it should sort of seem natural, but maybe you never really thought of it explicitly. But this formula is only true in radians. One way you can see this is in the graph of sine. Let's say this graph here is in radians, so its middle point here would be at pi. If we converted our domain here into degrees, this point at pi would suddenly jump all the way to the point at 180, and you could see that this whole graph would get very, very stretched. And what that would do to the tangent line, or the derivative, is that it would lower it to quite a dramatic degree. And I mean, you can see this stretching if you ever plug in sine into a graphing calculator and you accidentally have degrees still on. It's a very, very flat graph, so the derivative is going to be very, very different than this. Here we have the graphic I used to prove the derivative of sine and cosine in a previous video. We had a point here orbiting around another point at the center with a tangential speed of 1. Now, the radius of our orbit was also 1. And so we had some sort of angle t. Now, we used this angle t as sort of our measure of time, mainly because the tangential speed never changes, so the angular speed is never going to change either. And so our t is going to keep a constant rate, and it's going to keep good time. What we considered is what would happen at a certain time t if the orbiting point stopped orbiting and just continued on a tangent, like inertia, for 1 unit of time. Then the point would keep going on a straight line, and after 1 unit of time, since it's moving at a speed of 1, the tangent would have a magnitude of 1. That's how far it would go. Now, this 1 is actually equal to the velocity of 1, and this shouldn't be a surprise since velocity is just a measure of how far something moves in 1 unit of time. And so this distance here could actually be interpreted as our velocity vector, and because it's a velocity vector, it would have an x and a y component, both describing the speed of our x component and our y component respectively. So this y component would be the derivative of the y component of our position, or the derivative of sine. And this x component would be the derivative of our x position, or the derivative of cosine of t. Now the only caveat is you have to put a minus sign in front of this because the x component is pointing to the left while we're taking right to be positive. And so if you did some trig, you could realize that this angle here is exactly equal to t, and that because these are x and y components, this would be a right angle and this would be a right angle. And so because they share all equal angles and one of their sides are equal, these triangles are both actually congruent. Now since they're congruent, you can just match sides with each other and set them equal to each other, and you can easily find the derivative formulas for trig functions like that. Now in our proof we assumed that our tangential speed was 1, but this is actually necessarily true. If we looked at our tangential speed, well, it would be the ratio between the changes in our sector over our changes in time. And if we considered how much it changed from the x-axis up to an angle of t, then the change in s would just be the sector created by that because we were starting from 0, and the angle would be t, distance over time. But remember before that our sector in radians, or our sector is equal to r times the angle in radians. And now our angle in radians would just be our time t. And so we could say that v is equal to rt over t, and the t's obviously cancel, and the r is the radius, which is just 1. And so in using radians, we imply the velocity to be 1, which gives us this direct correlation. So that begs the question, what if we use degrees? Now before we can use degrees, we need to express our sector in terms of angles, degrees instead of radians. That's not too hard. Remember, our angle in terms of radians was equal to pi over 180 times the angle in degrees. And so we can substitute this now into our velocity, and we get that r pi over 180, and now our theta in degrees is our new time over time, and the times still cancel out, and our radius is still 1, and so we're left instead with pi over 180. And so this pi over 180 is our new tangential speed if we use degrees instead of radians. And so now, instead of this triangle having a hypotenuse of 1, it would have a hypotenuse of pi over 180. So now our two triangles are no longer congruent, but they still share the same angles. The magnitude of the sides don't change that, and so they will still be similar. And what that means is that if we scale one side up, we can scale all the sides up by the same amount. And if we scale, let's say, this side up by 180 over pi, we're going to get our hypotenuse of 1 again, and we're going to get congruent triangles again. And so if we draw what that triangle would look like, this would now be 1 because we're scaling everything up by 180 over pi, and now this would be 180 minus 180 over pi times the derivative cosine, and this one's going to be 180 over pi times the derivative sine. And so now we can match the sides again, and so this is the angle t here. So this matches with this matches with this, and now we can just multiply both sides by pi over 180, and we get that the derivative of sine is pi over 180 times cosine of t, and these are all in degrees, and then the derivative of cosine in terms of degrees is also minus pi over 180 times sine in t degrees. Now these new derivative formulas are a bit strange though, we have our familiar pi over 180 factor, which we saw when we went from degrees into radians. But notice here, we're going from degrees back into degrees. It seems that using degrees in a trig function is just an inherently more messier domain, and that radians describe the domain of a trig function better. Now, one place where angles and radians come up a lot is in physics, namely rotational mechanics. We mentioned briefly before the concept of an angular speed when we said that the speed at which the angle changed was constant, and a more formal way of writing this would be that the angular speed would be the derivative of our angle in terms of time. And we write angular speed like this. It is the rate of change of our angle in terms of time. Now, similarly, we have angular acceleration, which is how fast our angle is speeding up or slowing down. And we denote it with an alpha, and it is the rate at which the angular speed is changing, or the second derivative of our angular position. Now, if you ever look at the units for these two quantities, the unit for the angular speed is 1 per second, and for the angular acceleration, it is 1 per second squared. Now, we expect the second to be on the bottom, right? We have t squared and t, but this notation seems to imply that the unit for our angle is 1, just no unit. And in fact, that is. The unit for an angle is none. There are no units for angles. And you may actually see this written also like radian per second, or radian per second squared. So this seems to be saying that our radian is just as intrinsic as number 1. It's an identity. It transcends units like seconds or meters. So what we seem to be saying is that when dealing with radians with units and equations, that all it does to the units is add by 0 or multiply by 1. And so to really see this property in action, we need to get a better grasp on our angular acceleration and angular speed, specifically how they relate to our linear quantities. So the basis of this is going to be our sector equation. Now notice what happens if we take the derivative on both sides. If we take the derivative in terms of time, let's say, of our sector equation, well, that's just going to be our linear velocity, our tangential velocity. If we take the derivative on this side, well, the radius is constant, so it comes to the other side, and the derivative of our theta is how we defined our angular speed. Now we can repeat this process again. If we take the derivative on the left side again, we get our angular or linear acceleration, and if we take the derivative on the right side, the radius comes out again, and the derivative of our angular speed is how we defined our angular acceleration. And so now we have a way to get from our angular quantities into our linear quantities, and it's again just by multiplying our r, and it seems that radians is really living up to the name radians. Now, one place in physics where you shouldn't be surprised that radians come up is in circular orbits, and the specific example I'm going to be using is Kepler's third law. Now, you don't actually have to understand everything I'm going to do to derive Kepler's third law. All you have to really understand is where radians come up. And so, if we had a circular orbit, and we had a planet of mass n here, and then something orbiting the planet of mass little n, and the distance between the two bodies' center of masses was r, then the force of gravity would be g being some sort of constant, proportionality constant, n times m, those being the masses of the planet and the body orbiting the planet, and over the radius squared, the distance between the body's center of mass. Now, for any orbiting body that's moving with a constant speed, it will experience a centripetal force that is actually exactly equal to the mass of the body times the velocity squared over the radius of its orbit. Now, the force of gravity acts directly perpendicular or directly parallel with the radius of the orbit and perpendicular to the tangential velocity. And so it's never going to have any effect. That's a horrible V. So it's never going to have an effect on the magnitude of the velocity. It's just going to change the direction of the velocity. And so we are going to be seeing an exact circular orbit, and this force centripetal is going to be equal to the force of gravity. And so we can set these two equal to each other. Now the masses cancel out, and this radius can be multiplied over here, and it cancels out the 2. And so now we have the velocity squared equal to this big constant, right? Because g, m, and r is never going to change. Now, notice what we said our velocity was. Our velocity was r times omega. And so now we can replace this into here, and we have to square it. And we get r squared omega squared equals gm over r. Now we can divide both sides by the r squared, and we get an r cubed over here. And now let's think about what our omega squared is. The linear velocity is going to be a constant, so the angular velocity is also going to be a constant. So to find the angular velocity, we can just find the average angular velocity. And so the average angular velocity is going to be how far it moves in one revolution over its period, which is the time it takes to do that revolution. And so what that's going to be, it's going to be 2 pi, it's going to be how the angle it completes in one revolution, not how far it travels in one revolution, over the period squared is equal to g big M over r cubed. And now we can just square both sides and then bring the r cubed up here, and then we get that r cubed over t squared is equal to gm over 4 pi squared. So here we have proven that our period squared is directly proportional to our radius cubed, because if you take the ratio between them, it's going to equal some constant. Now, this is actually the exact proportionality constant between them. So if you knew the period of orbit, and you squared it, and then you multiplied it by this whole constant, and then took the cube root, you will get the exact radius of orbit. And in this process, we relied heavily on the radian. We put a lot of trust into it. Here, we said that the whole angle of revolution was 2 pi over the period. But if we used a different way of measuring angles, we could have gotten a completely different number here. And we would thus gotten a different number down here. And so this proportionality constant relies completely on the radian. And you can actually double check this result if you started again from this point. From this point we had that velocity squared is equal to gm over r. And now another way of, since the linear velocity is constant because the force is acting perpendicular, this velocity is also equal to the average velocity, like our angular velocity was equal to the average angular velocity. And we would have gone in, and we could have written this as how far it would have traveled in a period over the period, where the period is how long it takes for it to travel one revolution. And so that's going to be the circumference 2 pi r over the period squared equals our constant here. And now we can just do some algebra. We can square this and then bring the r squared down to the other side, or actually bring this r up and bring the 2 pi down, that being squared, and we get that r cubed over t squared is indeed gm over 4 pi squared. And so this is exactly what we had here. And notice the only point of departure was that we used velocity instead of our omega, but we still got our r squared here. If we just ignored this r squared, we would have had 2 pi over t squared, which is our angular velocity squared. And so with radians, we have these three equations, and they allow us to encode the ideas of circumferences and sectors without ever actually having to explicitly think about them when we're dealing with the angular quantities. We could just think about it in terms of angles, and we don't actually have to worry about converting things or any messy stuff. There seems to be a nice duality between angles and the sector they bisect. A unique angle bisects a unique sector, and I say unique because if we add a revolution to any angle, we're going to get the same effective angle. And so we can say that our angle is proportional to whatever our sector length is. But there's nothing holding us back from just saying that those two quantities are equal. Since they're so closely related, all we have to do is specify a specific radius. And we choose the unit radius of the unit circle just for convenience when scaling. The radian has this seemingly cosmic power to be used so haphazardly in equations when dealing with linear quantities or angular quantities. And this is only because the definition of the radian captures so fundamentally the relationship between the angle and the sector that it bisects. The radian is what the angle should be, the value of the angle should be. There's something truly 2 pi-ish in a full revolution. So I think there should be a greater appreciation for radians. They allow us to multiply linear quantities and angular quantities without having to put much thought into it. What they're really doing is they're translating between angular quantities and linear quantities. The radian is pretty much the real number system's interpretation of an angle.